So Google just released something pretty big. They're calling it TurboQuant. It's a compression algorithm for AI that reduces certain memory requirements by at least 6x and delivers up to an 8x speed increase. But here's the kicker, all with zero accuracy loss. The zero accuracy loss, that's the thing that is kind of strange to hear. It's so good, in fact, that it received a validated Weissman score of 5.2. The reaction of the panel was kind of wild. Everybody clapped. Wait a minute, that's the Silicon Valley TV show. Okay, so the Weissman score thing was nonsense, but the rest of it is true. All right, so let's talk about it. Let's dive into what the heck is happening here. I'm still remodeling this place, so I do apologize. It's like that joke, how many people with ADHD it takes to remodel a room? What was I talking about? Oh yeah, so Google releases TurboQuant. The headlines are huge. People are saying it's the algorithm that could crash NVIDIA's memory business. Tons of memory chip stocks drop. The whole thing's a bloodbath. What does this all mean? Let's dive in. How much of this is true? How much of this is hype? Let's take a look at, first and foremost, what is it that they actually figured out? To understand what Google built here, we need to take just a quick second to learn about how large language models and the transformers work on on the inside. Because behind every simple chatbot, there's actually a fairly complex system that tries to figure out what words mean. So first and foremost, if I asked you, what is it? What didn't it want to do? Where was it? That might be a little confusing because you have no context for what it is. I can tell you that it was the eighth word in the sentence. That still doesn't really clear it up. You need some context about it. Now, if I said the animal didn't cross the street because it was too tired, all of a sudden, you know a lot more about it after reading that sentence. What was it? It was an animal. What didn't it do? It didn't cross the street. Why? It was too tired. So it went from pretty meaningless to now the word it contains a lot more information about what we're talking about. I can just say it and you know exactly what I mean. The whole breakthrough with Google and attention is all you need paper with transformers. A lot of it had to do with this. It needed to learn what words mean based on what the other words around those words mean. So each of those words has some connection, some relationship to all the other words. And every time it reads a sentence like this, it jots down those connections or relationships. It kind of calculates them and it stores them in this little cache, if you will, so they can retrieve it and look at it later. So it doesn't have to reread everything all over again. The way that you remember what they already read is through this KV cache. K stands for key, V for a value. So as it's reading all the sentences, it stores them in this key value cache. You can think of it as like a little folder. Let's pretend that this is a folder. And so for our previous example of why didn't the animal cross the road because it was tired, let's say we're creating this KV cache for the word it. We would have some sort of a label here on the front of the folder telling us what's inside of it. And then we have all the stuff inside of the folder, all the meaning and all the data and everything. So for the folder it, the label would say very simple things. Nothing with deep meaning, just simple tags, you can think of it, so that the model later is able to kind of pull it off the shelf if it needs it. It would say things like it's a singular pronoun, it's the subject of the second half of the sentence, etc. So that would be the key, and the value is all the stuff that goes inside the folder. This is all the stuff that actually links that thing to all the other words, therefore creating meaning. So what's inside the folder, it's like, well, the word it represents animal from earlier. It's the thing that is tired. And that's how large language models, how they understand what words mean is just through relationships to other words. So as a man is to a woman, a king is to a what? A queen. Or big is to biggest, as small is to what? Smallest. So I think that's super simple for everybody to understand. But now just envision that this is happening in a 3D space. So you can imagine it as maybe like a lot of stars in space, each with its own location that you can represent on the X, Y, Z axis, right? It's a certain amount of units up and to the right and whatever. So X, Y, Z, you can determine the point of anything in a 3D space. Okay, so imagine you're asking me how to get to some office. Like let's imagine the office is here in this skyscraper and we're located here. I would tell you go 2 blocks, whatever, east, I guess this would be. Then you go 3 blocks north and then go up to the 3rd floor, right? So I'm go this much this way, and then this much up. So I'm kind of giving you a block by block directions, right? Go left, go right, go up, etc. But if you think about it, I can probably point you to it in a different way, literally by pointing. I can say, there it is, and point at the building, right? It's right there. I can point at the building and at the exact office up on the top of that building and say, it's 500 feet away. Now you have to agree that this would also be a way to show you where exactly that thing is located, pointing directly at it and telling you it's this far away, which would be extremely weird if that's how people gave each other directions. But for the context of large language models, this actually makes a lot of sense. And that's literally how Google describes what they're doing. This is from the article they published on it. They're saying PolarQuant. By the way, on this umbrella they released, there's PolarQuant and then there's a TurboQuant. So they're both part of the same thing. So PolarQuant is a new angle on compression. You see what they did there? So they're saying instead of looking at memory vector using standard coordinates, right? So we're talking about those kind of locations in space and the relationship between two concepts or words that indicate the distance along each axis, right? So 2 blocks this way, 3 blocks this way, 5 floors up, right? So that's the distance along each axis. They're saying PolarQuant converts the vector into polar coordinates using a Cartesian coordinate system. This is comparable to replacing go 3 blocks east, 4 blocks north with go 5 blocks total at a 37-degree angle. So this results in 2 pieces of information: the radius, which signifies how strong the core data is, and the angle indicating the data's direction or meaning. So if you kind of look at this chart, right, you have age up and down, you have gender left and right, right? So like an adult, if we go this way, it's a man. If we go this way, it's a woman. If we reduce the age, it's a child, or to the left, it's a boy, to the right, it's a girl, infant, pop quiz, hotshot, what's over here. I hope you're getting this because me pointing where it is, it tells you kind of the length and the angle that should indicate to you what word goes there, or at least like the meaning of it. Here we put grandmother, right? Here we might put grandparent. So you see how you just pointing at this coordinate, you can kind of infer the meaning that I'm trying to convey. So with this new Google breakthrough, instead of going like from here to here, you would go down this much and then left this much. We just point an arrow there, and that shows both the distance and the direction. And they continue here, because the pattern of the angles is known and highly concentrated, the model no longer needs to perform expensive data normalization step because it maps data onto a fixed, predictable circular grid where the boundaries are already known, rather than a square grid where the boundaries change constantly. This allows PolarQuant to eliminate the memory overhead that traditional methods carry. All right, so PolarQuant is pointing directly at the thing instead of step-by-step directions. KV cache is that key value cache, that folder where the models, as they're reading text, they're kind of taking their little notes on it. They're putting it in folders with labels and they store them. And later, when you get to later in the text, they have to think about, oh, what does this word mean specifically? What other knowledge do I have about this word? So they look through their folders, they pull out that folder with the right key, right? They open it and they look at the values to get that deep meaning data about whatever it is that they're talking about. I'll give you an example. Remember that new Google blog post where they said a new angle on compression? Now, rereading it, you probably find this absolutely hilarious. Why is it hilarious? Well, because now you realize that that's how they choose to sort of compress the data. They use the angle indicating the data's direction or meaning. So now you understand that when they say angle, they mean it both literally and figuratively, as in, like a new view on it, a new angle on it, and also a literal angle. In order to understand that joke and find it hilarious, your brain had to pull out the little KV cache folder, look through it, and see, oh, I get it now. Okay, I hope that was helpful, because I like to know exactly what things mean before we actually look at what happened. Because if you just see a bunch of words that you might not be familiar with, or you kind of know what they mean, but not exactly, you see a whole bunch of them just thrown together, it's confusing. You don't really get as much data out of it. Your KV cache folder doesn't get quite as detailed notes in it. So with that said, what did this new TurboQuant algorithm, how well did it sort of work? Well, they tested on a whole bunch of open source models, Google's own Gemma, but also Mistral, Llama, etc. And they were running it on NVIDIA's H100 GPUs, right? So these are real models running on real hardware, real GPUs, and here are the real numbers that they got. First of all, it's a 6x reduction in KV cache memory. So it takes 1/6 of the memory to pull the stuff out of that folder for later reference. At the same time, it had an 8x speed up, so it's pulling that stuff out 8 times faster than it did before. Now, this doesn't necessarily mean that the model is 8 times faster. It's just that specific process is 8 times faster, but those two numbers are pretty huge for that process. And finally, and this is what the kind of the final piece that you put in together, where this goes from pretty good to just mind-blowing. because we're always seeing and hearing about different algorithms and breakthroughs that makes things faster and more efficient, finding ways of doing something that saves memory. We're all familiar with, images, right? You might take a raw image on your camera and it's giant. The file is gigabytes. It's very heavy, right? But then you turn it into a JPEG and it gets compressed, and you can compress it more, less, depending on the trade-offs between, how big the file is, how fast you can open that file, and how much of the actual content that you want to keep. Is it okay if it's ever so slightly not as crisp, not as sharp? You don't want to be waiting for 10 minutes to send or open up an image. But usually as you're compressing it, you're losing something. Smaller, faster means the resolution is a little bit less. So this is why this is kind of crazy, because there's zero accuracy loss. They've tested it on various needle in a haystack tests, meaning they give it tons of large documents of a lot of text, and then they try to find specific meanings out of it. Not specific words like you could with, hitting Control F and then just typing in the word, like specific meanings and little nuances that are hidden in there. So what does this mean as far as what does this actually mean for companies running these models? Is it one of those things where it seems amazing on paper, but when you put in production, it's like, oh, 1% efficiency improvement? Is it one of those things? No, this is more like 50% cost reduction. So if you're an enterprise running large language models at scale, your cost savings would be estimated around 50%. You cut the cost in half. And attention is very expensive, right? And I don't just mean for people with ADHD, I mean for large language models and for other neural networks that are running on that transformer architecture where it uses attention. It's very compute intensive. So if you've got a GPU sitting there and it takes an hour to run a task, then you cut, how much memory is required. You increase the speed at which it's done. Well, that means things get cheaper. API calls get cheaper, faster, more requests per second for any given GPUs, and the ability to run longer context without hitting hardware limits. So for inference costs, this is in effect basically kind of right away. Running frontier models get 50% cheaper, basically kind of immediately. And this isn't like a little marginal improvement. This applies to every prompt, every API call, every chatbot response, every agentic workflow. That's important. So there's no model retraining required for this. There's no fine tuning. This is you're just switching it in. The model stays the same and you lock in that faster speed, that discount. This is a big deal for context windows. So if you had some models that were topping out at a certain context window because of hardware requirements, that constraint is lifted or increased. So now on the same hardware, if a company has a certain number of compute, a certain number of GPUs going burr, they might have certain context window limits. This effectively increases it. That means longer code bases, processing various long documents, larger conversation history, etc. So what does this mean for NVIDIA and GPUs? Well, if you have a company running on some amount of GPUs, let's say you had a GPU that was maxed out running one large model. This effectively means you can run more models on there or larger models. So this is a direct multiplier of NVIDIA's infrastructure. It's like in video games where they go, this thing gives you plus 20 to int intelligence. This is what NVIDIA just got, a plus 20 to int, or whatever the number is. It's a direct multiplier to its compute efficiency. What does this mean for Google? Well, Google's server costs, they drop. Running, for search, for example, like the search API and inference, that drops. Everything gets cheaper, faster, etc. The economic advantage of having a bunch of GPUs or TPUs, although they ran the experiments on GPUs, so they used NVIDIA's H100. And so that's what got us the 6x reduction in memory and the 8x increase in speed. Google's TPUs may be different, but I'm sure it's similar. But the point is, if you're sitting on a bunch of hardware and a bunch of compute, you just multiplied how much you have effectively. Now, you might be confused about the whole TurboQuant, PolarQuant. They also mentioned some sort of a quantized Johnson-Linden-Strauss thing. So what it is TurboQuant. So that's what everybody's calling it. This is the big thing, the umbrella thing. But underneath it, there's two pillars or two parts to it. The first one is more or less exactly everything that we've discussed here, right? And so instead of giving step-by-step directions, you just point and tell it how far away it is. That pointing, that's the PolarQuant method. That's the compression method. So that's the thing that really does the heavy lifting in terms of the speed and the memory reduction requirements. That's PolarQuant. But there's a second part of it, which is, I gotta say, might be just as interesting, maybe more. And that is that quantized Johnson-Linden-Strauss algorithm, which is what eliminates the hidden errors. So TurboQuant uses a small residual amount of compression power, just 1 bit, to apply the QJL algorithm to the tiny amount of error left over from the first stage. So that quantized Johnson-Linden-Strauss algorithm, basically, it's like an error checker, but it's super tiny, super fast, very small. So it eliminates any bias from the compression. It improves the accuracy. Again, the accuracy, there's zero loss from running this. So maybe that first thing, PolarQuant, maybe it has some tiny compression, something lost due to compression. But the second thing, the QJL, it, just checks those little errors here and there, making sure that everything's perfect. Together, those two things are the TurboQuant. So this news comes out. What happens immediately after? Stock market bloodbath, or at least for certain chip stocks. SK Hynix down 6%, Samsung down 5%, SanDisk down 5.7%, Western Digital down 4.7%, Micron down 3%. So the market logic is, if the memory requirements to run these AI models fall 6x or whatever number less, that means people will obviously use less chips, right? The demand falls. Now, I obviously would not bet on this being the case for just a number of reasons. I mean, the main counterpoint, you've probably heard this one before, the Jevons paradox. It's basically saying when the efficiency of using some resource increases, meaning it becomes cheaper, more abundant, it's not that you necessarily use less of the resource. The use of the resource might actually go up because now there's more use cases for it. You might choose to use it a lot more for other activities. If gas is expensive and you're trying to avoid driving, and all of a sudden the cost of gas drops to 1/10 of what it was, you might actually start driving everywhere. You might start taking road trips. If you're hot, you might just turn on your car and sit in it with an air conditioner, etc. You might attempt to start using your car to mow the lawn. I don't know. You might find some new novel application for it, or maybe decide to upgrade to an SUV, whatever. You're going to find ways to use more of that thing because it got cheaper. Making these models better, faster, more efficient with memory at no loss in accuracy is not going to lead to companies going, oh, I guess we don't need as many of these GPUs lying around. No, what's going to happen is people will find more and more insane uses for various large language models. A lot of them are going to be very useful, obviously, but the cheaper stuff is, the weirder the use cases get. Imagine going back in time to when there was some famine, people were starving, and explaining to them, carving pumpkins for Halloween. Right? It's like, yeah, we take perfectly good food, we carve it to make it look scary, then we put it outside until it rots. Just imagine having that conversation. How would that go? Okay, so to wrap up kind of like the big points here, TurboQuant is software. No new chip, no new retraining, no new model, no fine tuning, none of that. The leverage that each dollar spent on compute is increasing. Now, keep in mind, this is for inference, so this is not for training the models. That's a little bit different, but for production, for stuff, tokens rolling off the factory floor, so to speak, it's getting a lot cheaper. So we saw something similar happen with the DeepSeek moment. This is kind of like the Google moment, I guess. I think this is terrific for Google because they have tons of infrastructure. This is just making it cheaper, faster, better to use it to produce stuff. Every efficiency improvement for Google is just pure margin. Is this good or bad for NVIDIA? Now, I'm not a market analyst. Don't ask me. I have no clue. With that said, I mean, I guess maybe someone out there might make a good argument for the fact that NVIDIA, because of the constraints, maybe squeezes a little bit more money out of everything, where if things weren't as constrained, if everything became a lot more efficient, maybe, I'm not saying that's the truth. I have no idea. Again, I'm not sitting there calculating the actual numbers and the margins on everything and all of that. But I know this is great for example, Google, who have their own in-house TPUs. It's great for everybody running large language models and other similar AI models at scale. By the way, if you have a good idea of how this affects NVIDIA versus other hardware companies, if it's something that's not as quite obvious as it is on the surface, definitely let me know. I mean, my call here is Jevons paradox. Price goes down, use cases go up. If I'm missing anything, free to post in the comments. I'm curious to know if there's some insight here that maybe not everyone's seeing. But the other big winners are, well, us. I mean, specifically if you're using agents, if you're using something like OpenClaw, I mean, right now, the issue is that, Anthropic, for example, if you're using Claude and you're using their, the authentication key for Claude code, which you're not supposed to, I'm not saying you should. I'm sure nobody's doing that, right? But the point is, if you're maxing out your quota and you're paying $200 a month for it, if you had to pay for it yourself through standard API pricing, that would be a lot more expensive. I'm not quite sure how much more, but I don't know, 10x more. So you'd be paying $2,000 a month, maybe potentially a lot more than that. So a lot of the token usage is subsidized by these companies. So if everything gets cut in half, number one, it's great for them. They can give us even more, right? Maybe they lose less money on the inference on the tokens, or they just double how much they're willing to provide for the same price. And the actual, I guess, power users really win big from this. Andre Karpathy in his latest interview was talking about how it's like one of the skills that everybody needs to learn is to like use every token that their quota allows them. If you have a certain amount of tokens for the 24-hour period or for the week or for the month, just max it all out, turn those tokens into some sort of a valuable output. Well, with something like this, effectively that sort of a possible valuable output just got doubled, assuming you're already running up to the constraints, to the limits of that. One thing that I really want to point out to everybody that I think everybody needs to understand, and it's important that we at least get that this is happening. Google posted the Attention is All You Need paper that described the transformers. Most of the companies that we see right now competing with Google exist in part because of the publishing of that paper. And also now all the people that are going to benefit from this technology, from TurboQuant going out there, the only reason we're all going to benefit from it is because Google published it. They posted it out there. Sure, it benefits them. They get more use. It benefits their company. But there's a lot of businesses that if they were sitting on something like this, why would they publish it? It gives them the ability to cut costs on their models, on their hardware. They don't have to tell anybody else about it. They can just, take those profits, take that advantage, put extra pressure on the competitions. That's the regular playbook, but they published it just like they published the Attention is All You Need paper, just like they published all of the other stuff in this field that they're publishing, like the continuous learning paper, just everything. So I don't know what you want to do with that, but I mean, come on, you gotta, give it up to Google just a little bit. They're doing some good work here. All right, so let me know what you think about that. By the way, Anthropic's new Mythos model, they were saying it's very expensive to run and it might be not viable. With this, it sounds like it just got half as expensive to run. So I'm not sure if that plays into Anthropic's decisions of when they're releasing it or how they're releasing it, but that's also there. If you made it this far, thank you so much for watching. My name is Wes Roth, and I'll see you in the next one.